AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, good morning. Good morning, everyone, and welcome to the AI for Earth and Sustainability Science webinar series. I'm Maria Piles from Universitat de Valencia, and this will be our fifth seminar of the series. The series is curated by the ELIS unit JENA and the ELIS program on machine learning for climate and earth system science. And my colleague Gustav Camps from Universitat de Valencia and Markus Reinstein and Joachim Dessler from Max Planck Institute in Jena. They are co-conveners. And we have the pleasure of having today with us Dr. C.J. Zhang. He is an hydrologist working on the interdisciplinary application of machine learning in hydrology. And his research interests cover many aspects of the application of novel intelligent techniques, especially computer vision and interpretable deep learning, from camera-based rainfall data acquisition to using intelligent techniques to empower hydrological modeling capabilities. He will be showing us today a lot of these. He completed his PhD at the National University of Singapore and is currently a postdoc researcher at the Helmholtz Center for Environmental Research. His current research focuses on integrating hydrological theory and machine learning to better understand the water cycle and stream events under climate change. Dr. Zhang also works to foster the application of knowledge integrating machine learning to earth science questions more broadly, and is dedicated to developing a general framework for physics AI data hybrid modeling. So the talk today is about hybrid modeling. So the title is Towards Hybrid Physics AI Hybrid Modeling in Hydrology, Opportunities and Challenges. And I hope this brief intro is enough. And then I'll leave the room to C.J. Zhang. Thank you.
Yeah, thank you for the kind of introduction. I think I can share my screen for the presentation. Yeah, can you see a screen?
Yes.
Okay, thanks. Okay, Today, I'm going to talk about the development of physics AI hybrid modeling in hydrology, and I have been working on it for a few years. Today, I will share my perspective on it with some of my experience, and I hope you will find this talk interesting. Let's begin with the motivation of developing an integration scheme that brings together AI and physics. The goal of the hydrological model is to simulate and understand the behavior of a hydrological system, including the process such as the precipitation, the evapotranspiration, infiltration, runoff, and groundwater flow. Traditionally, these models range from simple conceptual models to more complex physics-based models, depending on how much physics knowledge is included. In recent years, as machine learning has become more popular, we have also seen the rise of data-driven hydrological models. And compared with the traditional process-based models, they can typically achieve similar or even better predictive performance. And here we can use a spectrum of the model transparency to show the range of hydrological models. Basically, the process-based model and the data-driven models are at the opposite ends. And for a long while, people have thought that the process-based model and the data-driven models are two distinct ways of studying hydrology. In the ideal case, we could use either ends to model the hydrological system. And the different ends can give us useful information from different perspectives. But the thing is that in reality, both data and knowledge are not perfect. So they may have some limitations to both types of the models. And here I use the saturation of the blue color to represent the degree of how much of the knowledge we know, and the red represents that of data. And in reality, we are usually in the middle region to build the models. For the process-based model, the main problem is that some physical process may be simplified or missing or underrepresented, and it will make the model unable to fully capture the system's complexity. And for the data-driven model, the main issue is that it usually has the risk of the bad extrapolation ability because the model may overfit on the limited or noisy data. Obviously, one possible way to address these limitations is to the available data and the available knowledge at the same time. That is what we call the integration model. The integration scheme aims to merge the data, the physical principles, and the machine learning algorithms in a whole, such that it can make full use of both of the strengths of the established knowledge and the machine learning in a unified framework. On the one hand, the knowledge in the integration scheme can constrain the learning process of the machine learning to the meaningful and physically consistent patterns instead of learning from scratch or without guidance. On the other hand, the machine learning part of the integration scheme can provide the process-based model more learning units so that the possible knowledge gaps can be filled by the data-driven insights. And in principle, the integration scheme can benefit hydrology in two aspects. The first aspect is that the integration scheme can provide us reliable and accurate predictions. And second aspect is that the integration scheme can provide some new insights or new hypotheses to enrich our current knowledge base. And the predictions and insights can benefit from both physical consistency and the learning ability from big data. And I will explain them in more detail later. And nowadays, the synergy between the physical components and the AI models has become a hot topic in hydrology and earth science, and it opens up a new and huge opportunities to better understand the complex natural system. And in my view, there are two immediate keys to making this strong vision to a reality. The first key is how can we effectively incorporate the knowledge into the AI models? And the second one is how can we extract the learned patterns from the AI model as new knowledge? And in the following slides, I will share my thoughts on the two topics and discuss some of the recent research in the field. The first topic is to explore the ways of encoding knowledge into the AI models. As I previously mentioned, combining the physics-based models and machine learning models can be a promising way to use both scientific knowledge and data. Although this is just a relatively new concept in hydrology and earth science, but as there are already a number of good studies on the subject to date, and based on the form of the available knowledge and the computational objectives, we can group the integration methods into 4 categories as outlined by this excellent review paper. And the categories include the physics-guided industrialization, physics-guided loss function, physics-guided design of architecture, and hybrid model. And in the following, I will provide some examples for each category and including some of my own work and show how they could fit into a broader landscape of the hydrological research. The first category is the physics-guided initialization. When we train the machine learning models, the parameters of the machine learning models are usually initialized randomly. But this can lead to the model getting stuck into some local minimum. And to avoid this problem, we can use physical knowledge to inform the initialization process. This means that we can provide the model with a physically consistent good starting point before it sees any real observations. And the classical method to do that is to pre-train the models with a large amount of the physical simulation data, and then fine-tune it with limited observational data. And during this process, we may even freeze some layers to keep the learned patterns unbroken. And by doing so, the model can achieve satisfactory performance even with a reduced training sample. For example, in this study on applying deep learning to answer forecasting, the researchers overcame the data limitation by pre-training the model using the CMAP5 output and then fine-tune it using reanalysis data. And the comparison shows that the prediction per scale can be improved due to the pre-training. And second category is the physics-guided loss function. This approach is one of the most common strategies for integrating physics and AI, and it has been applied to a wide range of problems in hydrology and earth science. And the basic idea is to include the physical constraints in addition to the existing machine learning loss function as a penalty term. And by doing so, this strategy, in theory, can reduce the solution space of the machine learning models to ensure the consistency with the physical laws. And the popular application of the approach is the lake temperature prediction. And in the study, a known relationship between the water temperature, water density, and depth is included into the loss function as an additional physics-based penalty. Moreover, this approach has been extensively explored in PDE-related work. And here, the loss function is modified to ensure the model outputs satisfy the governing equation and initial and boundary conditions. Thus, it can guide the neural network to learn the solutions that satisfy the underlying physics when fitting the data. And here is a notable work from Albert Uphoff, who has provided a practical guide to the implementation of the physics-based loss function in environmental science applications. And the third category is the physics-guided design of model architecture. Although the physics-guided loss function and the physics-guided initialization can help introduce physical consistency, the machine learning model architecture is still a black box. And to address this issue, a recent research direction is construct new machine learning architecture based on the physics-based guidance. And this approach can make a black box algorithm more interpretable and more transparent. And the common strategy is to use the domain knowledge to specify the meaning of nodes and node connections. And a typical example of that is the mass conserving LSTM. Here, the researcher modifies the original node connections to enforce the mass conservation by design. And they have shown that the new architecture has a good predictive power and can provide interpretable representations in hydrological prediction tasks. And the fourth category is hybrid modeling. And it is a promising approach and is one I want to highlight. The first three strategies we discussed earlier focused on improving the machine learning models themselves, but the hybrid modeling aims to combine the machine learning models with the physics-based models in a more coupled way. Traditionally, the physical models and the data-driven models are two different modeling schemes with different modeling logic and language. And here I use a blue to represent the process-based model and red to represent the data-driven model. In the hybrid model, the physical model will be encoded in a neural network language using the computational vocabulary that is available to deep learning framework. In this case, although it is still blue, now it can be coupled with the red ones following the same language. And because of the modular design of the deep learning architecture, they can work in different ways. For example, the black box components and the physical components can run sequentially when we put the two components in a serial way. And in sometimes we can use the black box components to replace the subcomponents of the physical parts, as this diagram shows. And here I use a purple color to represent the combination components. And it is even possible to combine all the components in a more complex way in both theory and parallel methods. And in the following slides of this section, I will use examples from my previous work to explain how the hybrid model works for the hydrological modeling. And in the first example, we have explored an effective way to encode a lumped hydrological model into a deep learning architecture. And my strategy was used to a special recurrent neural network to encode the numeric process of a hydrological model, because there are a lot of similarities between the methodology, between the mathematical representations of the two model types. In the ordinary recurrent neural network, the nodes of the inputs, outputs, and states in the recurrent cell are usually connected as a perceptron. But in our proposed physical layer, we will specify the internal connections with the real physical expressions, and the network parameters, such as the weights and bias, are changed to parameters with physical meaning accordingly. And here I still use blue to represent the process-based model. And the two parts on the left and right actually are equivalent. They can do the same thing, but the only difference is that the right one is the model writing in a neural network language, and now it's a physical layer. And because of the modular design of the deep learning architecture, you can connect the different types of the layers like a building. And in this study, we add some ordinary neural network layers after the physical layer. And here we use the red color to represent the black box components. And the black box components are used to correct the possible mismatch of the between the output of the physical layer and the real observations. Also, to enable the model can be run in a regional manner, we prepare additional ordinary neural network layers to provide the catchment specific parameters from the catchment attributes, such as the soil and the vegetation properties for the cross-region learning. And in this architecture, both the physical components and the black box components can work well together, but they have their respective roles in the modeling procedure. Now let's examine the results. The left two maps show the stream flow prediction performance of the purely data-driven model and from the purely process-based model in around 600 basins in the United States. And the right map shows the performance of the hybrid model. And the warmer color indicates a better prediction. And as you can see, the hybrid model can outperform the partial model. And we found that the hybrid model can inherit the predictive power of the partial models and can adaptively adjust when to trust the data-driven model or when to trust the process-based model. Specifically, when the process-based model performs well, the physical part can dominate the predictions, and otherwise the data-driven parts will take over the prediction. In summary, the hybrid model can provide a better prediction than the partial models. In addition to improving the stream flow prediction, we found the hybrid model, the framework can provide additional benefits. For example, by comparing the left box and the right box in the figure, we can find the cross-region learning ability can be improved because we enable the parameter learning. It means that the black box components used for parameter learning can improve the prediction transferability in spatial cross-validation because it can map the spatially heterogeneous catchment attributes to catchment-specific parameters. Moreover, the parameters learned from the hybrid model can provide spatially continuous information about the hydrological behavior, such as the parameter of the decline rate of runoff and the parameter of the soil water storage capacity. And we found they exhibit a spatial pattern that generally follows the soil property of the United States. And this information may be useful for us to refine our understanding of the hydrological process, like how the soil property can impact the two parameters respectively, or what are the implications of the soil property to the hydrological process or hydrological systems. And as a final point, the hybrid model is also able to reason the unlearned variables after integrating the process-based model. We know that deducing the intermediate variable that are difficult to observe or impossible to observe directly is the value of using a process-based model. And in our study, although we train the hybrid model using only the stream flow data, the model can still accurately infer the snow water equivalent because it has integrated the hydrological knowledge. And the maps shows that the snow water equivalent inferred by the hybrid model has a very close spatial pattern with an independent observation data set from NASA. And the temporal variation is well reproduced on average. And all the results of above shows that the physical-based model and the machine learning models have worked well together in our unified framework. And the hybrid model is a good way to combining two types of thinking, that is inducing the new information and deducing from known knowledge. And in our ongoing work, we have further improved the hybrid model by incorporating a spatially distributed hydrological model that includes a river routing process to enable the spatial temporal learning. And after incorporating this model, we can even infer the spatially distributed variables such as the routed river discharge and the evapotranspiration from the hybrid model. And in the hybrid framework, a black box components showing by the red color is used to provide the grid-specific parameter learning from the grid-based static attributes similar to the previous study. In addition, we also use another black box components to replace the estimation of potential evapotranspiration in the hydrological model. The PET was generally just approximated by the empirical equations, such as the Pullman-Montes equation. And the estimation is typically an underrepresented process. And by replacing the estimation with a more representative black box components, we may better capture the physical process underlying the PET estimation and improve the overall accuracy of the modeling. And due to the time limitation, I will skip the details of our results, but I can see that our finding demonstrated that both temporal and spatial learning performance can be improved compared with the original hydrological model, because the hybrid model includes the data-driven parameter learning and data-driven sub-process learning in the hybrid model. And we can also find the data-driven PET plays an important role in the accuracy improvement, and the learned PET give us an opportunity to revisit the traditional estimation method, and it may have the potential to inform better estimation methods. Overall, enhancing the process understanding from predictions is one of the important value of such the hybrid model. And here are some additional examples of using hybrid models for hydrological modeling in the last 2 years. Regardless of which process-based models was considered, the basic idea are similar, that is to either use a black box components to replace some uncertain or unexplored, underexplored process to improve the modeling accuracy, or to provide parameter learning to improve the model generability. Overall, the previous slides have introduced several strategies for integrating physics and AI, but I wouldn't say which one is the best, because each has its own advantages and disadvantages. And the choice of the strategy would ultimately depend on the specific problem and available resources. For example, the physics-guided installation is the easiest one to implement, but the architecture and the learning process are still a black box, and the influence of the physics is just limited to the initial state. Similarly, the physics-guided loss function doesn't provide a clear explanation of the learning process. And the physics-guided design of architecture can be more interpretable, but it still requires a deeper understanding of the physical principles to design it. Among all the 4 categories, the hybrid modeling is often the most complex one, because it requires both the domain knowledge and machine learning expertise. But it's still my top choice in my study because of the flexibility with modular design of the deep learning. And it also has the potential advantage in process understanding when it is combined with post hoc interpretation. And I will present this topic in the next part of the talk. The next topic is about the ways of decoding knowledge from AI models. In recent years, there has been a growing interest in applying the explainable machine learning to decode knowledge from AI models. And the primary goal of the XAI is to provide insights into how these models generate the predictions and uncover the underlying relationship between features and the predicted outputs. And by using the XAI techniques in hydrological science, we can improve our understanding of the relationships and the patterns that underlie the machine learning. And the common strategies and applications of XAI for process understanding mainly include the feature attribution, the causal inference, the latent implementation learning, the counterfactual explanation, and all. But in this talk, I will only focus on the feature attribution because it is currently the most common and intuitive application in geoscience. And here I will use my own research as an example to demonstrate how XAI can benefit our understanding of the natural process. Specifically, I will discuss how it can be used to identify the river flooding mechanisms or drivers. We know that the different floods in a catchment often have different generation mechanisms, and traditionally, identifying the flooding mechanism has been very subjective. But our research explores using the XAI method to automatically infer them. And our methodology involves three main steps. The first step, we use a machine learning model to build a many-to-one predictive relationship between some meteorological variables, such as rainfall, precipitation, temperature, and day length to the river discharge. And second, we will use interpretation techniques to interpret the role of the inputs at their every time step in predicting each annual maximum discharge event. And this method can assign a series of feature importance score to the inputs for each flood sample, just like the heat map shows. And in the third step, now that we can get a bunch of feature importance values from all the flood events, from all the catchments, we can apply the cluster analysis to group them into several categories, and each category can correspond to one flooding mechanism. As a result, we identified 3 clusters in Europe, and they can correspond to 3 main flooding mechanisms in hydrology. That is snow-melt-driven flood, the recent precipitation-driven flood, and the antecedent soil moisture-driven flood. And we can calculate the proportion of the 3 types of floods in each catchment, and we find that the results are consistent with our knowledge about the climate distribution. And with the results, we can do many things. For example, we can examine the trends in flooding mechanism, and we find that the annual floods have been driven more frequently by the recent rainfall, but less frequently by the snowmelt in the recent decades. And this shows again the impact of climate change. The climate change can affect the flooding mechanism, and such changes in flooding mechanism can eventually impact the flood magnitude and seasonality. And it will have important implications for policy and future planning related to flood risk management. And all the above insights are based on the post hoc interpretation on deep learning models. And the above work is just an example, but there are actually many excellent studies in the area. Overall, the explainable machine learning technique have been widely adopted in various fields in earth science and hydrology, but the post hoc interpretation still face some practical limitation. For example, one of the most pressing problem is the spurious correlation learned by the machine learning models. And the misleading correlation may lead to a false understanding of the process. In addition, the explanation method often only just provides information about where the decision was made, but knowing that doesn't tell you the whole story about how the information was used. And the different interpretation method may generate different interpretation results, and it will be difficult to get a consistent understanding of the underlying process across different models and across different instances. And sometimes we may also face the risk of rediscovering known patterns. And this is because the patterns in the data that are easy to be identified may be prominent among all the identifiable signals. However, I believe these challenges can be partially addressed by using hybrid modeling. For example, the hybrid model can guide the learning process to focus only on the meaningful and physically consistent patterns, such that the risk of spurious correlation can be reduced. And the hybrid model can also provide a more comprehensive explanation, a story about the model behavior, and their insights are often more consistent with our established knowledge and generalizable across different instances. In addition, the hybrid model can effectively isolate the individual components to reduce the impact of the strong signals, and it will allow us to focus only on discovering the new phenomena or the patterns that we are interested in, because some insights into the specific relationships may be not evident when looking at the model as a whole. All right, in the final minute, let's take a moment to dive into the opportunities that the hybrid model may bring to the hydrology and explore the potential challenges as well. And based on the above overview, you may find the hybrid model may have a great potential to improve our understanding for the hydrological process. And let's take a conceptual model diagram I mentioned earlier as an example. Here, the different colors represent different components. We can combine the post hoc interpretation with the black box parameter learning, and such that we can explore the relationship between the local attributes to the hydrological responses, such as to investigate how the local attributes affect the hydrological responses and how the effects would vary under different conditions, and how dynamic attributes such as deforestation or afforestation could affect water distribution and extreme events. And by combining the sub-process learning and post hoc interpretation, it may provide us opportunity to identify which physical process are underrepresented and what information was missing in the knowledge gap. And for the overall modeling learning process, we can study how the dependence between the responses and the inputs evolved in the past and the future. Moreover, because as the deep learning architecture has a strong adaptability, it allows us to assimilate different data sources into the model, such as the remote sensing imagery, the ground-based sensor, and the social economic data. And the integration can lead us to explore the questions such as how the multi-source data can contribute to a better process understanding and how human activities would affect the hydrological processes and water availability. Despite the opportunities described above, I have to say hybrid model is not a master key for everything. In some situations, hybrid model may be quite useful, but in other situations, hybrid model may not be the best choice. And in my opinion, the hybrid model is particularly useful when both knowledge and data are partial, meaning that neither source alone can provide a complete understanding. And the hybrid model may be also useful when you want to incorporate multiple data sources or to address some knowledge gap or to enhance black box model interpretability. However, there might be some other situations where hybrid modeling isn't the best fit. For instance, when the physics process are totally understood, the traditional process-based model could be enough. And if you have got unlimited data with enough diversity, I think a large-scale deep learning model might be also enough. And in many cases, you have to weigh the costs and benefits before considering implementing a hybrid model, because it is possible that the case that you have spent a lot of time to make the process-based model couple well with the machine learning model, only to find the hybrid model doesn't offer substantial improvements. And this is particularly possible when data and the available knowledge don't complement each other. So it's crucial to figure out if hybrid model is really needed for your case and what your goal is before using it. Okay, I think that's time to wrap things up. In summary, the hybrid model can offer us an effective way to dispel the barrier between process-based model and the machine learning model. And the approach not only make our models more interpretable, but also improve their predictive capability and helps us for the better process understanding, particularly on the process which might be still unclear. And to make all this happen, I think it's critical to collaborate between the hydrologists, data scientists, and the machine learning experts. And our ultimate goal is to unlock the potential of hybrid modeling and make a real impact in the field of hydrology and geoscience. Finally, I want to acknowledge my research colleagues and collaborators that helped with the studies. And I want to thank all of you again for being here. Thank you.
Thank you, CJ. It was a very comprehensive introduction to the world of hybrid learning and hybrid modeling, and it was great that you guided us through the best of the one world and best of the other one. And I think you're like positioning in the middle that it's a solution for many problems in hydrology as you have targeted. And let me open the chat. So I'll invite all the people online to write their questions to CJ. But meanwhile, I'd like to ask you as an hydrologist, which would be the underrepresented processes that you would target with machine learning that we still don't really represent well? What physics are we missing?
Yeah, actually, I think, for example, just as I showed in my slides, we have used the machine learning component to replace the estimation of PET because this is relatively an underexplored process, and we can replace it with the more representative model that is the neural network model, and replace it in the hydrological model, and then run the models on the data and see whether the overall model performance have improved. If so, it means that the physical process may be underrepresented. And then we can even to use the post hoc interpretation technique to examine the learned PET and the relationship with the inputs such as the precipitation and temperature, and see what is the real relationship is. In that way, we can improve our understanding of the underrepresented physics.
Okay, so I guess there will be different parts in the hydrological systems that we could focus on. And then I'd like to ask about the use of observations, since we're having more satellite data, more in situ comprehensive data sets. So the higher spatial resolution and the higher temporal resolution we have the data, the better you can exploit it, right, with the hybrid models. But what do you think will be more important, spatial resolution or temporal resolution in the hydrological modeling that you are working on, or both? Would you go into, because you saw that the spatial, you were focusing on the spatial distribution of the river floods, right? Or the river routing and that, but that will mean that higher spatial resolution data will help you.
Yes, actually, yes. When we encode a spatially distributed hydrological model, we have the ability to assimilate the temporal spatial information into our model, and this can help us to further improve the model accuracy. But I think this is not the only target, and the more important one is that with the spatially distributed information, we can infer the spatially distributed variables as well, such as the soil moisture distribution, the evapotranspiration distribution, and we can use this information to inform the agriculture management and something else. Yeah.
Okay, so we have some questions on the chat from Luisa Luquesa. She said, good morning, thank you for your presentation. And the question is, how does one ensure parsimony in integrated physics and AI models? I mean, that they are not overdimensioned, especially in the data-driven part.
Okay, so it's a good question. So when we design this architecture, we have make sure we have a good balance between the physical part and the data-driven parts. If the hybrid model rely too much on the physical knowledge, we may lose the opportunity to learn from the big data. And if the hybrid model rely too much on the data, it may lose the benefit from the already known knowledge. So I have to say that depends on your question. So and it also depends on your purpose. Your purpose is to interpret the black box components, or improve the overall accuracy, or to improve or to identify the missing physics. So it can help you to balance which components in the is more in your model.
Okay. Yeah, it makes sense, but it's okay. I guess when you saw the different approaches, they were increasing complexity up to these hybrid models. But what is the computational cost? Is it very high as compared to a data-driven approach, or?
Sorry, my sound is not.
I'm asking about the computational complexity of these hybrid models. So you mentioned in your presentation that they are complex.
Yes.
But are they also very expensive in terms of computational cost, like more expensive than the data-driven ones because of the?
Yes. Yes, as you have to consider the cost and benefits to design such a hybrid model, and because maybe you have a very complicated physical model, and it will consume a lot of time to encode it in a neural network language and make it coupled with the machine learning model, but because it maybe already somewhat perfect, and it can make a good prediction enough. And in that case, the value of data may be not very have such improvements than the only use the physical model. So you have to consider it. But I have to say that to consider the complex physical model into the hybrid model, the important thing is to identify the most important process or relationship of the physical part, and which have the significant impact on the system behavior. And we can only focus on accurately representing this process in the hybrid model, but just simplify or approximating the less critical components. Yeah, that's
okay. Yeah. So there's a balance in there. Okay.
Yes.
We have a question from Peter Watson. I think it goes in that direction. He asks about the hybrid approach. What do you mean? Do you mean to take a known conventional model and encode it in a neural network structure? But which weights and activation functions are set to reproduce the model output? Or do you encode it any other way? Also, he asked if this technique is only applicable to differentiable models.
Yeah, actually, this is just encode the physical model into a neural network way. So the answer is the first. So actually, the hybrid model is just to use the physical model as a backbone, and use the black box components to fill that. Yeah.
Okay. But do you need to use differentiable models?
Yes, this is a differential models. Yes, exactly.
Otherwise, you cannot do that. Okay.
Yes, yes. Because actually, in my case, it's just directly differentiating the physical model and connecting them with neural networks. Yeah.
Okay. Okay. So answer is yes.
Exactly. Yes.
Okay. We have one more question from William Thao. He asks, from your perspective, to what extent the hybrid model could predict the streams, say for high temporal resolution, hourly peak flow?
Okay, so that depends on whether your data has such information to represent the high temperature resolution hourly peak flow, and whether the physical process can represent such a high temporal resolution. Because your hybrid model is just is a couple of the two parts. If your two parts have the ability to absorb such information, I think your hybrid model can also do that. But even though your physical model is not in such a high temporal resolution, I guess the hybrid model can still make a good prediction on the hourly peak flow, because the basic principle of the hydrological model is the water balance. So let's say if you have the high precipitation falling on the ground, and it can generate the flow, and if it satisfies the water balance, it can make a good prediction on that case.
Okay. So yeah, I guess if you combine the physical model, you have some chance of capturing the streams. Otherwise, you know, we perhaps we don't have the enough data on streams as they are occurring now. So I think this would be a field in which the hybrid.
Yes, that would be a value of the hybrid model. That is to reduce the reliance on the data. Yeah.
And then, you know, we don't have enough streams of the kind to train the model. So
yes. So it's just like a process-based model. It can make a prediction on the extreme flow, and so the hybrid model in theory can also do that.
Okay. Now I really like your results about extracting a snow water equivalent without using that data as input. So
yes.
Have you done any other experiments in that direction, like trying to learn some parameter out of the combination of the other data? And
yes, I have examined the evapotranspiration as well, and we find it may have some difference with PT estimation method using the empirical method. And we find such a difference is very interesting, because the PT the evapotranspiration estimation is challenging in the Amazon basin. But our study point out that, okay, so the traditional method may have underestimate the evapotranspiration. So this could be provide a new insight for that. And but this is it's our ongoing work, so we are still looking into it.
Okay, so I guess you're targeting specific questions, phenomena in which you can apply the hybrid, and then that it's beneficial. Because I guess you have also. I'm gonna ask about this, because we normally don't publish the things that don't work. But have you tried to apply hybrid modeling to some process that it really didn't work out because the physically based models were good enough?
Mm-hmm.
Put one example in which the hybrid model doesn't help.
And help in which case? Could you repeat again?
Well, one example in which the hybrid modeling is not helping at all. So you'd rather go with the physics only.
Yes, exactly. Yeah.
Did you find one of such examples? Could you, in the hydrological system, like some process that you targeted?
Actually, no, not yet, because yeah.
So at the moment, hybrid learning has always helped you,
Okay,
right?
yes. I
Okay,
also think so, yes. Thank you for the suggestion, yes.
that's good. That's good.
Yes.
Okay, we have one more question from Mitra. I wonder, when you discuss that data-driven model is enough in cases where data is huge and has enough variety, how can you tell you have enough variety of data?
Okay, so it means that it means the data have enough diversity. For example, for the hydrological applications, your data may include all the runoff mechanisms, and can see all the different climate regions and different topographic regions, and it has such diversity to make your data have enough transferability to this region to another region. So if so, I would say the data would be a high enough variety of data. But in some cases, because we have many engaged basins, so we don't have information from some specific types of the runoff generation. So I think from this view, the data is still imperfect. That's why we should use the hybrid model, to use the physical knowledge to help the model. Yeah.
Okay. And now this is just a comment that in our first seminar, in the first seminar talk of the series, we were discussing also the use of kind of the physics and machine learning. And then we were discussing the use of reinforcement learning as a kind of habit learning, but it's not in your taxonomy, right? Because it would mean like having one different approach in which you have an agent that tells you that, hey, this is wrong. It is not having, conserving mass or energy or something.
Yeah.
What do you think of this? This will be another classification, or maybe it falls in the hybrid directly, or?
Actually, I think this, I couldn't say that is a kind of as a hybrid model, because when we say the hybrid model, I would say the use the physical components and the neural network components will work together in an end-to-end learning system, and we will balance the using of the physical part and the machine learning part, make them together to deal with some specific task. And this is a physics AI integration.
Okay, so it falls in the last category.
Yeah, I think so. Yeah.
Okay, good. And I have one more question, if there's not more in the chat. Okay, that's about the use of, the most simple use of the physical of the data in the physical models is just initialization. Right? And you said that helped predictions, but also you said it accelerated the training.
Yes.
I'm curious, but by what degree? Because this is relatively simple to do, right? You just get an initialization value. Was it like a high degree of acceleration, or do you have an estimate of how much you could improve the training time? If you
Actually, I couldn't give you an exact number, but because in principle, if you initialize the model structure with a good starting point, it in theory can converge just in a short time. But how much? I think it depends on how complexity of the model, right? So
yeah,
if you have a simple model, okay, so it's very easy to find all the possible, because the solution space would be very small. But if your model is complex, the solution space is will be large, and in that case, you initialize the model with the physical knowledge can help. I think it would be.
It can help more in case that you have like broader, but in general, I found that is relatively easy, and we could recommend it to to the practitioners,
Yeah.
since we were saving time and for a more sustainable AI, which is one of the topics too.
Yes, I think so. Yeah.
Okay, so I think if there's no more questions on the chat, I'd like to thank you for being here today with us. I really enjoyed your talk and I think we can now go to the to this other session in which people can ask you on the chat.
Yeah.
It's called Yes.
Yeah. Thank you.
Is it okay? Okay, so thank you, and see you in the other room.
Yeah.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
you.